All right, filters. Okay, I realized that conceptually last time's lecture on impedance was probably the most confusing thing we've done so far, because it was kind of straying the farthest into uncharted territory relative to what you've done in either physics or system dynamics. That was kind of supposed to be the setup. Today the application hopefully is going to make that make more sense, and we'll see why it was worth it, but we'll see. So again, remember our end goal here is we might have some electrical signal, and electrical signals can have different frequencies, right? Just like mechanical vibrations can have different frequencies. Again, I think driving in a car is a really good example. It might be a bunch of bumps in the road. You want those mechanical vibrations filtered out so you don't feel them as the driver and you have a nice smooth ride, right? Same deal with electrical signals. You might want to filter out high frequency noise, or you might want to filter out lower frequency noise. And I forgot to mention last time, for example, in the US, power lines are at 60 hertz, right? There's a 60 hertz, that's why you can get a flicker from fluorescent lights. I think in some other countries it's 50 hertz, but whatever. That's as electrical frequencies go, 50 or 60 hertz is kind of low, right? Like a lot of electrical things are in the kilo or megahertz range. So sometimes you might want a high pass filter that actually gets rid of that lower frequency noise because you're just looking at the higher frequency signals and you want to get rid of noise from the power outlets in the wall. Okay, so that's our objective, is how do we do that? Okay, and we are going to do that by using things we have learned about so far. A resistor, a capacitor. We're going to send a sine wave in, and we're going to measure V out over here. But last time we learned about impedances, right? So we already knew that we had our Ohm's law, V equals IR, and our capacitor equation, I equals C dV dt. But now, just kind of writing down stuff we've seen before, we have this weird, magical, imaginary quantity called impedance, and we know that for a resistor, the impedance is just the resistance, but for a capacitor, this nebulous quantity is this weird thing, 1 over Cj omega, where again, C is the capacitance, omega is the angular frequency of the sine wave in radians per second, and then J is a square root of -1, which we're using in electrical engineering because I is already taken for current. And I'm just kind of waving my hands at the imaginary part there. We're mostly just going to be looking at magnitude in this class. So again, here I'm kind of just showing the magnitude or amplitude of these waves, but I did talk about how they're also shifted in phase. And if you took to system dynamics, you saw that with Bode plots and everything. For the sake of time, we're kind of ignoring it here. Okay, so my goal right now is to find an expression for the magnitude of V out over Vn as a function of R, C, and omega, right? So this is going to be, this magnitude or amplitude, whatever you want to call it, is going to be frequency dependent. I want to find that function. I'm going to do that using impedances. And using impedances means I don't actually need to write out any sines or cosines or anything. Okay, that's where the argument that, like, oh, this actually makes the math easier because you don't have to bother with trig functions comes in. So I'm going to kind of redraw my circuit with just boxes to represent impedances. I don't care what they are, whether it's a resistor, a capacitor, or an inductor. Still have my sine wave V in, still have V out over here. I still have all those equations I just wrote down. I also have, from last time, I know that impedance is in series add. And I know that impedance is in parallel, so we kind of treat them like, they behave like resistances in series and parallel, right? So impedance is in series add, and impedance is in parallel add inversely. Given everything I just wrote down, try to find this expression. I'm going to open it as a poll everywhere, okay? And we'll see kind of if people start making progress on it. I'll leave it open, and if not, I'll kind of provide some hints to keep you going. But I guess one hint to start, remember how we did this for a voltage divider just with resistors at the beginning of the semester. Okay, if you go back through your notes, you should have that. I don't remember how many lectures ago. We did this with resistors, okay? You knew Ohm's law, you knew these rules for resistors, and we were able to find an equation for, okay, what is V out or V out over V in as a function of these resistances. right? So similar process, but now we've got impedances which are frequency dependent. So see if you can do the same thing and find that expression. I'm going to open the poll everywhere. There you go. Okay. Try to do that, and depending on how much progress we make, I'll kind of help nudge people along. Here is hint number one, if you're having trouble getting started. Since these are in series, the current through them must be the same. That's the other thing, that even though impedance is this weird nebulous concept, again, remember from last time, KCL and KVL still apply, right? So if I have two impedances in series, Z1 and Z2, then the currents through them must be the same. And if I were to have two impedances in parallel, Z1 and Z2, then the voltage across them must be the same. So that still applies for impedances as well. And so if you can kind of hinting at how we did this for a voltage divider, if you combine those two impedances into a single equivalent impedance, then you know the current there has to be the same as the current here when they're broken out. Okay, so kind of remember how we did this with resistor network analysis. So again, I'm going to stop there for now. And I guess this isn't really a hint, because I realized I didn't put in any answers that still had it there, but since I'm asking you for a magnitude, the J should be gone, right? So that the magnitude of a complex number in the real and imaginary plane, right? If I ask you to find the magnitude of a vector like that, say A, B, that magnitude is just the square root of A squared plus B squared. So there's no, the magnitude is entirely a real number. There's no imaginary component to it. But again, I didn't throw in any fake multiple choice answers that still had the J there. Okay, we're still only at about 65-ish responses, and I think we had more than that for the first question. So again, kind of another hint here. And so if we're combining those in series, that's going to be equal to the impedance of the resistor plus the impedance of the capacitor, which is just the resistance R plus 1 over C J omega. And the other thing I didn't write down from last time, just my general definition of impedance is just impedance equals voltage over current. So here, this is my ZEQ. That equals my voltage Vin over my current I. And then just like we did for the voltage divider originally, right, I can solve for this current I here, and I know that is the same as the current through each of the individual components up there. Okay, so I think I'm going to, if you're not sure at this point, just guess, and I'm going to close this and kind of go through the rest of the derivation. 5, 4, 3, 2, 1, deactivate. Okay. Correctness, about 2/3 of you got that right. A was the correct answer. Okay, so I'm going to kind of go through the rest of the derivation here in case you didn't get it. Okay, so this is having combined everything into a single impedance. Using my definition of impedance, Z equals V over I. I'm going to rearrange that to, and this is going to get a little messy the way I lay things out on paper here. Solve for I equals Vn all over R plus 1 over C J omega. Right, but then up here, I know that also applies to each of these individually, right? So for ZC here, I have ZC equals V out over I. Rearrange to solve for that I, it's V out over ZC. And now I know that this I has to be equal to that I, right? So I can set those equal to each other. We'll do that down here. So Vn over R plus 1 over C J omega equals V out over ZC, which is 1 over C J omega. Okay, so I'm getting there. I now have an equation with most of the things I care about, right? I have V in, V out, R, C, and omega. I still got the J in there, but it hasn't, because I haven't rearranged things and taken a magnitude yet. Okay, so if I rearrange that to solve for V out over V in, which is what I am getting at, then I get 1 over C J omega all over R plus 1 over C J omega, right? That looks kind of messy with the 1/overs in the numerator and the denominator, so I don't have to, but can choose to, and this is how you'll see it if you look the formula up in a textbook. You can always multiply a fraction by 1, right? So I'm going to multiply anything by 1. So I multiply by Cj omega over Cj omega to cancel out the ugly fractions, and then I get 1 over 1 plus RC J omega, which is almost there, but that's not a magnitude yet, right? The J is still in there. So if I take the magnitude of that expression, the magnitude of a fraction is just the magnitude of the numerator over the magnitude of the denominator, then I get the final answer, which is the magnitude of V out over Vn equals 1 over the square root of 1, I'm sorry, there's an extra parentheses in there I didn't need to draw, but 1 plus RC omega squared. Square root of that whole thing. Cool. Box that equation because you need it for the homework. Okay? Even if you, again, hopefully have some understanding of kind of where it came from, and it's just not just a magical equation that popped out of nowhere. The point is we can look at this equation, and I'm going to need to, I'll wait a second, and I'm going to redraw that on the next piece of paper because we ran out of room here. that equation tells us what the frequency dependence of this circuit is going to look like. Okay, so I'll give you a second to catch up if you kind of needed help tracking through the algebra there. But again, end result, this one is still a complex number, so there's a phase component to that we were just kind of ignoring. We're taking the magnitude 1 over the square root of this quantity that depends on both the resistance, the capacitance, and the frequency of the input signal. Okay? I'm going to bump that up and start drawing again on the next page here before I move this one out. So I'm going to copy that equation over. V out over V in equals 1 over square root 1 plus RC omega squared. Okay. Just like we did with the individual impedances for a capacitor and inductor, we can look at that and go, okay, what happens as omega goes to 0 or omega goes to infinity? Okay, so as omega goes to 0, right, this term goes to 0 and this just becomes 1 over 1. Right, so the magnitude of V out over V in approaches 1, so the output is the same as the input. Right? We're not changing it. As omega goes to infinity, right, the denominator gets really, really large, so this fraction approaches 0. Okay, so V out over V in approaches 0. And if we were to make a graph of this, with omega on the x-axis and magnitude of V out over V in on the y-axis, usually this is, oh, sorry, I don't need to slide up here. This is done with the frequency on a log scale. Again, this is probably how you saw the Bode graphs in system dynamics, where sort of go 1, 10, 100, 1,000, and so on, to kind of give you a bigger picture of what the frequency response looks like. It's going to start out pretty flat and then kind of taper off, right? And get smaller and smaller and smaller as omega approaches infinity. And that's why this is called a low pass filter, because it is passing or allowing through the low frequencies, right? And filtering out the high frequencies. And you can select the value of the resistor and the capacitor to kind of determine where this drop-off is. So I have a different color pen here. And ignore like the 1, 10, and 1,000 there. That was just kind of explaining what a log scale is. I don't have numbers for R and C in this problem, so those aren't specific to this problem. But the cutoff frequency is usually defined as where this magnitude has dropped to, I always mess the exact number up, 70.7%. So when you've attenuated it by about 30%, or the output is only about 70% of the input, that is equal to 1 over RC. So it's the inverse of the time constant. Okay, so you can choose the resistor and capacitor value to determine where that cutoff frequency is based on the frequency of the noise you want to filter out. Okay, you say, oh, I'm getting electrical noise on this circuit at 10 kilohertz or something, then okay, I'm going to pick an RC value that gives me a cutoff frequency below that, so I can keep the frequencies I care about, but I want to kill or get rid of 10 kilohertz. And I believe, I forget exactly how the problems are worded, but this is basically what homework 3 is going to be asking you to do, is, okay, pick R and C values to design a filter with this cutoff frequency. Okay, and again, using the kind of squiggly line example, that is going to mean that in this case, we have some electrical signal with both high and low frequency components to it, assuming appropriate choice of R and C values for the right cutoff frequency. That's going to get rid of the high frequency components and keep the low frequency components. And again, that is called a low-pass filter. So think of, again, even if you don't remember, as with everything else, I don't expect you to remember that equation, right? That equation is something you can go look up. But as an engineer, there are things, if you're in a conversation with someone, you should know what they mean without having to go look it up. So you should know what a low-pass filter is. Okay? You don't want to have somebody mention low-pass filters in a job interview and just go blank because you have no idea what that means. So conceptually, right, you might not have to remember the 70.7%, but you should remember the shape of this graph and this concept. Okay? That formula you can go look up. Remember this. Okay. Question, and I guess, so I know you did frequency response and system dynamics. Did you talk about filters like this or just, okay. So again, it's not, this is just the top half of a Bode plot. Okay, there's nothing special or different about it from what you saw in system dynamics, and I feel like we tend not to talk about mechanical things as filters, but again, you can literally I think low pass is, a car suspension is a very good example, okay, or anything where you want to filter out vibrations. Maybe in civil engineering, like earthquake response would be a better example, where you want to filter out the frequency of the ground shaking so it doesn't destroy your building, right? There are probably other examples we can think of. If anybody's really into audio stuff, speakers like subwoofers and tweeters and speakers that are better at different frequencies, right? You might want to filter out, we're only going to send the low frequencies to the subwoofer. So I think that, again, the car suspension is the first thing that comes to mind to me, but you can probably think of lots more non-electrical examples where this concept of a filter applies. Okay, so questions on anything we've done for the last 10 or 15 minutes or however long it's been? Yes?
Sorry, so it's at the bottom of the last page. But the equation, like in the bottom left corner, V in over R plus 1 over CJ. Yeah, that's just setting the currents equal to each other in the two branches, right?
Correct. So the question was, what is this? This is taking, and I kind of didn't organize my space on the page well. That is setting this equal to that. So we know that this is the current after you've combined the impedances, right? And then when you expand it out again, so remember this is kind of how we did the resistor network analysis, where you collapse it all to a single resistor and then expand backward. So that's the current after we've combined the impedances, and then this is the current just through the capacitor, and then setting those two currents equal. So that could end there. I was like here, I still wrote this as ZC. Here I wrote it out as 1 over CJ omega, but those are interchangeable.
Got it.
All right, thank you. Your device ran into a problem and needs to restart. Terrible timing. Okay, well, maybe we won't get to do the second poll everywhere today. Okay, other questions on the whole low pass filter thing? Yes?
So does that mean we need to have our ratio of voltage on the left hand side to avoid the high frequency, or?
I don't totally, so you don't need to do anything with the voltages to avoid high frequency. You get to choose resistor and capacitor values to get rid of those high frequencies for you. Does that make sense again? So I guess I didn't totally understand. Can you repeat your question? I don't think I totally understood what you were asking.
I think I sort of get what you're saying. It's I don't need to change or control my voltage ratio to some range to avoid the high frequency, right?
Correct. You do not need to do that. So assume that you have an electrical. So if you have an electrical signal coming from something, coming from a sensor, a radio receiver, something, and that signal can have some noise on it. Okay, just like if you, this is going to make me feel really old. Did you guys at least grow up listening to the radio, or have you only ever known Spotify? So people, okay, I'm not that old yet. So you can get static on a radio, right? Fuzz, right? That static is coming from ultimately, it's electrical noise, right? So a speaker is an electromechanical transducer. It is taking an electrical signal, converting into vibrations, which then get converted to sound, right? If the original electrical signal is noisy, then it's going to add extra little vibrations to the speaker that we will hear as kind of static or fuzz, right? So that's just one example. Later in the semester, you're going to use Arduinos. Arduinos can have analog sensors that output a voltage that is proportional to some physical quantity, okay? Light, speed, temperature, whatever, and that there's electrical noise in the environment, so that signal might have a little fuzz or noise to it. Okay, so this is assuming that you are getting a voltage from something and that you are designing a filter to get rid of the little vibrations and noisy parts so you get a nice smooth signal. Does that make sense?
What's the meaning of that W?
Of where?
You see it?
Here?
No, like the first, second page on the top. You said the W?
Here?
Yeah, what
That's omega for frequency. So that's the angular frequency of the signal in radians per second. Okay. Did I see a hand start to go up?
Yeah,
up
so
front?
just out of curiosity, would the high frequency vibrations then just be like dissipated as heat by the resistor?
So the question was, would the high frequency vibrations be dissipated as heat by the resistor? I haven't thought about this from a power perspective, so I am not. That gets complicated. So again, if you took circuits, there is a whole section of stuff we're ignoring here about how power works when you're not ignoring phase. So if you ever hear reactance or reactive power, this is a giant rabbit hole we could go down. Kind of like, again, think of forget circuits for a second. Think of the spring mass damper as an example, right? When you stretch the spring, you get energy stored in the elastic stretch of the spring, and then you get some of that energy back in kinetic energy as it rebounds on the next. But some of that energy is also dissipated as friction, right? Similar here, where there is power dissipated by the resistor, but there's also some power stored in the capacitor that kind of comes back on the next swing. So if you look at this wave though, right, like some of that energy can be stored in the capacitor and then come back from the capacitor. So some power is dissipated in the resistor, but I don't think it's technically correct to think of all of that as being dissipated by the resistor, right? Because some is stored in the capacitor on each cycle. Does that make sense? Okay. Anyway, we are not going to ask you in this class. We're not going to ask you to do power calculations for any of the filters. So technically, you don't have to worry about it. But if we went back to RLC circuits, this also implies, again, think of a spring and a mass trading energy, kind of like a capacitor and an inductor trading energy. You can have an RLC circuit where the resistor is the only part that actually dissipates power, right? Otherwise, the capacitor and the inductor both just store power. So for any circuit with some combination of resistors and capacitors and inductors, the resistors are, in the idealized mathematical model, the resistors are the only elements that dissipate power, right? In reality, nothing is 100% efficient. Capacitors have a small leakage current and some resistance to them and all that. But that is kind of way beyond the scope of what we're covering in this class. Okay, I saw another hand behind you. Or was that the same question?
I answered.
Okay. Other filter questions? Or sorry, low pass filter questions as I log back in here and try to pull everywhere up again. Okay, any other questions on the low pass filter thing? Okay, give me 1 second. Okay, next question. Cool. What happens if we flip the capacitor? Oh, I am not even drawing on the document cam. Okay. What happens if we flip the capacitor and the resistor? Okay, put the capacitor first, put the resistor second. Otherwise, it's the same setup. Being as a sine wave, we want to know what is the magnitude of V out over Vn. Give me a second to get back to baseball everywhere. Okay, same process. All I did was flip the capacitor and the resistor. What is V out over Vn? Pull everywhere up. You can probably make an educated guess as to if the first thing we did was called a low pass filter, what this one's going to be called. But without giving away the equation, can you kind of go through the same derivation and figure that out? And we've got a little over 20 minutes left, so I probably won't give this one quite as much time because I want to have a little time at the end to talk about some other stuff. Bless you. Okay, I'm going to give a hint to speed the process along. So, remember, again, back when we did this for voltage dividers, we kind of slogged through and figured it out manually, but then at the end of the day, for a voltage divider, we just knew that we had this formula, V out over Vn equals R2 over R1 plus R2. Since I said you can kind of treat impedances like resistances, you can also just jump right to this formula. Okay, where instead of, with resistances now, we have ZC, ZR, the impedances in Vn and V out. For this specific configuration where I just have two impedances, I can just apply the voltage divider formula to that, but with impedances. So I can write Vn over V out equals ZR over ZR plus ZC, and go and skip that step of, okay, I'm going to collapse them into an equivalent impedance and solve for the current and then expand again and set the currents equal. It's faster if I just do that. Okay, so if you were doing the combine them and set the currents equal thing, that's fine. But if you were kind of stuck on getting started again, or if you want to abandon the current procedure because that's more annoying, you can just jump right to that equation. Okay, let's give it like another 30 seconds. We're at 85 replies. I think we had maybe 95 in the previous one. Okay, let's go 10. Five, 4, 3, 2, 1. Deactivate. Okay. So skipping straight to, oh sorry, let me check the correct answer in this case was E or whatever, I forget how many in it, but that's the last one is, which again about 70% of you got. So going through this, for those of you who might have gotten the algebra wrong, skipping straight to the voltage divider equation to make life easier. I'm going to plug in my impedances, so I know the impedance of the resistor is just R over R plus impedance of the capacitor, Cj omega. Again, I don't really like having that fraction within a fraction because it's ugly, so multiply the whole thing by Cj omega over Cj omega. Then I get RCj omega over 1 plus RCj omega. That is the complex fraction, not just the magnitude. So if I take the magnitude of that whole thing, then I get the magnitude of V in over V out equals RC omega over the square root of 1 plus RC omega squared. So it looks very similar to what I had before, except instead of a 1 in the numerator, I now have an RC omega in the numerator. And so I can ask the same question, well, what happens as omega goes to 0? Sorry, V out over V in. In that case, numerator of the fraction is going to go to 0, but the denominator is going to go to 1. So V in over V out is going to go to 0. And as omega goes to 1, or sorry, as omega goes to infinity, then V out over V in is going to go to 1. Okay, so I have the opposite of what I had last time, right? At very low frequencies, the output's going to go to 0. At very high frequencies, the output is just going to approach the input, right? So if I draw a graph of that, it's pretty much just mirrored, where it goes down to 0, and then it's going to approach 1 as it goes out to infinity, and that's why this is called a high-pass filter. Okay, again, let me box the equation. Don't expect you to have that equation memorized. You can go look it up in 10 years. In a job interview in 1 year, you should remember the difference between a high-pass filter and a low-pass filter, right? And I'm going to slide up. Again, since we aren't going into as much depth just due to time as you would if you took a full-blown circuits course, there are lots of other types of more complex filters that you can get by combining more elaborate combinations of resistors and capacitors and inductors, right? So say you only want to let a very specific frequency through, right? So you don't just want to let all low frequencies or all high frequencies through, you just want to let a narrow band through. And again, I'm glad that most of you know how radios work, because tuning a radio, right? You don't just want to let all frequencies above 97.3 FM in, you only want to let 97.3 FM in, right? So you can have, and I still don't understand that very first poll everywhere we did where I asked what you were most excited about in the course, somebody said bandpass filter, so like, here's your moment, bandpass filter. Okay, rather than just letting high or low through, you can kind of have a band, right? That's why it's called a band pass filter, and the steepness of that band is going to depend on what you want. You know, again, with radios, this is why there's spacing between the stations, right? Every time it goes 97.3, 97.5, it skips 1, right? Because if those get too close together, then you start getting interference between stations. So I think this is interesting because in mechanical engineering, this is usually bad, right? Like, you don't want your physical thing to vibrate so much that it falls apart. But in electrical engineering, many times you do actually want, okay, we want a very strong response to this specific frequency. Question?
On the previous page, why did we choose to go max with V in over V out?
Oh, sorry, that's just me. That should be V out over V in. Is that what you're asking? Yeah, sorry about that. I messed that up. I mean, multiple places. So V out over V in. Anywhere I mess that up, that should be V out over V in. Sorry about that. Okay, I think I fixed all of them. Okay, thank you for catching that. Okay, so bandpass filter. You can also have sort of the opposite of a bandpass filter called a notch filter, where again, maybe you don't want to block all high or all low frequencies, but you kind of want to get rid of frequencies just in one specific range. Again, 60 hertz is a good example, where maybe, again, you have some, again, think of audio applications, right? Human hearing goes down to around 20 hertz, right? So if you want to get rid of 60 hertz noise on your audio equipment, you don't necessarily want to just do a high pass and kill, say, everything below 100 hertz, because then you're getting rid of your 60 hertz, but you're also getting rid of lower frequency sounds that are still in the range of human hearing, right? So maybe for that you would just want a notch filter that's kind of targeted right at 60 hertz to get rid of the audio noise. And you can, again, with more and more complex systems, have combinations of these where, okay, we have a band pass that's letting several different frequencies through, or a notch filter that's killing multiple certain frequencies. But doing the math for all of that, again, is kind of beyond the scope and time commitment we have for this class. But conceptually, add this to the list of things like, okay, I should at least know what those graphs look like on top of a basic high and low pass filter. And again, for whoever is really excited about bandpass filters, you actually get to build one on the homework if you haven't gotten there yet. So I hope you have fun. Okay, we are going to start op amps on Wednesday, but rather than starting a totally new topic on the Friday before break, I'm just going to end there. So have a good break. As usual, I will be here for questions. Thank you.